the free energy, therefore, it follows as minus kBT ln, which is minus kBT n ln V minus n ln lambda t minus ln n factorial plus 1 over v to the power n logarithm of dr1 drn product over pairs ij 1 plus fij. With it is understood that I is less than j. And then we close this bracket for this. Thermodynamic pressure. First interest is to look at the thermodynamic pressure. If you know how is the derivative related to the Helmholtz, so how is thermodynamic? So our first interest is to calculate the thermodynamic pressure from the free energy F, because this gives me the equation of state, and that is what I am after. So this equation of state is what I am after. So I know the relation is minus del F del V, temperature held constant. So let's do that. So this minus that you see over here and the overall minus that is contained in the free energy makes it a plus. So that I have kBT n by V. The second term does not have any volume factor, so you don't have to worry about it. The third term also does not have any volume factor. It also does not come into the picture. But the last term does have this. So this has to be del del V of ln 1 over V to the power n dr1 drn product over pairs I less than j 1 plus fij. Now it also you have to note one thing, that fij is dimensionless and dr1 drn divided by v to the power n is also dimensionless. So this makes the picture very consistent. One does not have to worry about dimensions at every step of your calculation. N kBT over V. If I take this outside, this becomes V over N del del V of ln of 1 over V to the power n dr1 all the way up to d of rn, and I have product over pairs I less than j 1 plus f of ij, and then we close the bracket. We did not close the bracket here, so we close the bracket over here. To shorten the notation and to make our life a little bit more convenient, what we will write over here is that this is going to be del del V of some free energy F bar. Where F bar is now ln 1 over V to the power n dr1 drn product over pairs I less than j 1 plus fij. So let's see, did we do anything stupid over here? Did we miss out any n factorial? I think this is fine. In fact, what additionally we can do here is to take the n, to keep this v and absorb the n in f bar. Now, assume that the gas is weakly interacting, which means that you could be at a high temperature or a low density. In either of these situations, if it is a low density system, then the two particles rarely see each other, right? So most of the time it's like almost a free particle system, but sometimes they have to collide when they come within the interaction range. So if you recall that the potential that we are looking at, the soft core potential had something like this, and this one was 2 to the power 16 sigma, and if you take this to be 2 sigma or even 2.5 sigma, the potential is already vanishingly small. So for a low density system, most of the particles are far away. Only when they come within a distance of 2.5 sigma or 3 sigma, they feel some kind of a tiny bits of interaction. Otherwise it's vanishing, otherwise it's all zero. Similarly, in the high temperature limit also you have the same situation. So what happens? It means in such a situation that this quantity beta V of Rij, because you have a high temperature, beta is very low, minus 1 is equal to F of Ij, right? So this factor is almost 1, so that Fij is very tiny. So Fij is negligibly small. Under such a circumstances, we can write down this product over pairs with I less than j, 1 plus Fij. If you now see that this, if I write down explicitly F12, 1 plus F13, 1 plus F14, so on and so forth, if I expand, then the first term obviously is going to be unity. The second term is F12 plus F13, so on and so forth, all possible pairs you have, and then you have F12, F13 plus F13, F14, so on and so forth. So we will truncate our series over here because F is so small. We have 1 plus sum over I less than j, all pairs Fij plus order of F square, which we ignore. Now let's look at the integral of this quantity. dr1 drn, product over pairs with I less than j, 1 plus Fij is going to be integral dr1 drn 1 plus I less than j, all the pairs you are considering, f of ij, plus something which is of the higher order, which we ignore. The first one is very trivial to do. The first one is nothing but v to the power n. The second one is integral dr1 all the way up to drn sum over I less than j Fij. So clearly I can rewrite this as I less than j dr1 drn Fij. Let's pick up one term. We have seen this, right? We have expanded this. Let's say I'm just looking at the term f12. So that this integral now, just look at, if I write down the sum explicitly and I pick up only one term, this means let's say I have dr1 drn f of 1, 2. So you're looking at r1 and r2. Particle number 1, interaction between particle number 1 and interaction with and particle number 2. Here I can clearly separate out dr1, dr2, the rest of the integral dr3 all the way up to drn f of r12. This f function does not depend on the other coordinates 3, 4 all the way to n. So this can be integrated out and all of this is going to give you a volume v. So this is going to give you v to the power n minus 2. There are n minus 2 integrals over here. So this comes out n minus 2 integral dr1 dr2 f of r12. But now I know how to handle such a measure. I will go to the center of mass coordinate, which is r1 plus r2 divided by 2, assuming they have the same mass, and the separation r, which is going to be r1 minus r2 divided by 2. The Jacobian of the transformation is unity, and you are going to get v to the power n minus 2 integral d of r small r f of r. This is a scalar r, please note that, whereas this is an integral over a vector. This part I can easily integrate because the integrand does not depend on the center of mass coordinates. So this center of mass coordinate is also allowed to have the whole of the volume, and so you take out another factor of volume and this becomes v to the power n minus 1 integral dr f of r. Correct? Now this we did with one such things. So if I write down this, open up this sum, I will have f12 plus f13 so on and so forth. I could have chosen f13 here. If I choose f13, just very briefly I want to write down over here, if I choose f13, I can carry forward the same argument that I did, f of r13, and again you will see that I'll have dr1, dr3, f of r13, the integral over the rest of the coordinates is going to give you n minus 2, and this again is going to give you dr f of r, so that you are going to have v to the power n minus 1 d of r f of r. So what does it mean? It essentially means that if I look at the structure, which was v to the power n plus sum over I less than j pairs integral dr1 drn 1 plus, sorry, not 1 has already been integrated over, I will have f of ij. This effectively means that I can just pick up one such integral, and how many possible pairs can I have? NC2 number of pairs I can pick up from the system, from these n particles, so that I can just replace this sum by n into n minus 1 by 2, which is essentially your NC2 integral v to the power n minus 1, and so I replace the sum by this and just pick up one of the typical integrals that I have by choosing one pair. So I have v to the power n minus 1 integral dr f of r, v to the power n. So that In the thermodynamic limit, n minus 1 is approximately n, and this becomes v to the power n plus n square v to the power n minus 1 dr f of r. Let's see. So this integral is therefore integration product dr1 drn product over 1 plus f of ij pairs with I less than j is going to be this. Then this means I'm interested in this quantity. So let's write down f bar. I'm interested in f bar, which is going to be 1 over n, and then I have log of 1 over v to the power n integral dr1 drn product over pairs I less than j 1 plus fij. This was the quantity that we had defined. It's exactly over here. And I know that now integral has now evaluated to be only in the low density or high temperature limit as 1 over v to the power n times v to the power n plus n square over 2 v to the power n minus 1 dr f of r, plus whatever you will have is going to be order of f square, and then you close the bracket. So this is 1 by n ln 1 plus v to the power n is n square over twice v integral dr vector r f of r plus order of f square. Again, since f is very tiny, so that we are looking in the low density limit, I can just take this expansion. Use ln 1 plus x is approximately equal to x to write down this as 1 over n so I'm going to have 1 over n n square over twice v dr f of r plus order of f square, right? So that this implies del f bar over del v is going to be 1 over n del v of n square over twice p d of r f of r plus order f square, and this gives me 1 over n minus n square over twice v square integral dr fr plus higher order terms. I can simplify this further to write down this as n over 2v square integral dr fr plus higher order terms. But I also, so with this, it is understood that I'm only looking at the low density limit or high temperature, right? Good. So now let's go back to the expression for the pressure. The expression for the pressure was very simply this. So the thermodynamic pressure was nkBT divided by V Now, before we do that, let us just be a little bit more careful. What we have done over here is essentially we have taken order of f square. But in reality, this is not the case. What one has to look at is, if I keep the term which is Fij, the next order Fjk, which means that you are not only choosing pairs but I, j, and j and k, and I and k. So 3 of them are being chosen, which is going to be NC3. So n into n minus 1 into n minus 2, this is n factorial, n minus 3 factorial divided by 3 factorial, and you have 1/6 of this. Now clearly you see that this is going to be of the order of n cube. So when you say that you ignore this f squared term, essentially you are looking at a term which is of the order of n cube. So even though I have written it of the order of f squared, just to emphasize the fact that I am ignoring terms which are of the order of f squared, in reality that translates, because after all you are going to integrate over f, you are going to integrate over this coordinate. So in reality it essentially means that there is an order n cube term which you have neglected. So these all would mean that I have neglected an order n cube term. So then P equal to nkbt 1 plus v del f bar over del v, which is going to be nkbt over v 1 minus, let's substitute v times n over 2v square integral dr fr plus higher order terms. Let's go back a step, and you see that I have a 1 by n. So if this was of the order of n cube, then you realize that this is of the order of n square, right? Now one can also refine the argument a little bit more by saying, look, I will have an integral which is Fij, Fjk. For example, this term will give me F12, F13, and I will have dr1, dr2, and dr3. Rest of the coordinates I can integrate over to give me n minus 3. And one of them, just as you will have v to the power n minus 1, you are also going to get a volume from here. So this is finally going to be v to the power n minus 2. The next order term is going to be v to the power n minus 2. If you now take v to the power n common, then this is going to be of the order of n cube. The first term was of the order of n square over v. This becomes n cube over v square. So that you are going to have a term which is going to be n square over v square. And when you write higher order terms, you essentially mean a term which is of the order of n square over v square. I think it should be v cube. So let's see, where did we make the mistake? Yeah, correct. So this is going to be n cube over v square, but then there is a derivative with respect to v, which is going to give you n square over v square, because you not only have divided by 1 over n, but you have also taken a derivative with respect to the volume. Now this is going to be n square over v cube, not this one. This is going to be n square over v square, since you multiply v cube of 1. So this higher order term is going to be an order of n square over v square. Up to here it is going to be a order of n square over v cube. And once you multiply with v, you're going to get order of n square over v square. And we can close this. So then we have nkbt over v 1 minus half n by v times dr f of r plus n by v whole square plus terms which are on the order of n square over v square. Now, identifying n by v as the density, I have this as rho of kbt 1 plus b2 rho. Remember, Fr has a temperature dependence, Fr has a beta factor, so this is going to be b2 times T times rho plus b3 times T times rho square plus. So the equation of state takes this particular form. This is what is called a virial expansion. And this quantity, the first correction over the ideal gas result is called the second virial coefficient b2 of t as minus half integral dr f of r. Given the form of the potential, you can evaluate this coefficient. The first is always the ideal gas result.